Alright guys, if you were to focus on one problem this chapter, this would be the one. Hopefully you've given more than one a shot, but this problem is most similar to what your lab and your lab practical will be like. So it says a ball is rolling across the table with a velocity of 3.5 meters per second. So what's going to happen is that velocity is all going to start in the horizontal, is how most problems say it. So your velocity initial is entirely in the x at 3.5 meters per second. Now because it's entirely in the x, your velocity initial in the y is 0. Now what's going to happen is time passes, gravity is going to make it get greater in the y, but the velocity in the x will actually stay that way the entire duration of the drop. Now when we're talking about projectile motion, we are always talking about before it collides. It's when it's in free fall that matters. So for that reason, we would never say that the velocity ends with 0. Okay, that's the impact that causes it, and external force is applied. So what we need to do is make our XY table. It's like a dead spot on my screen over there. Alright, now we need to talk about everything we know in our X and everything we know in our Y. Alright, I'm going to label my diagram here with the distance that it gave us. It said that it lands 1.5 meters away from the table. So that is actually going to tell us our delta X. I should move that over. My delta X is 1.5 meters. My delta Y is how tall the table is. And it doesn't tell us, and it's actually looking for it in part B. So delta Y is what we're going to look for at one point here. How long is it in the air? Now because we know the distance it goes in the x, and we know its initial velocity in the x, and we know the acceleration in the x, we can find that, and we can also utilize mostly our y. Alright, and it lands 1.5 meters from the base. We know acceleration in the x, because it's in free fall, is always going to be 0. Acceleration of the y on Earth in free fall, always going to be negative 9.81 meters per second squared. Now that tells you that your delta y is also going to be negative because it's dropping. Remember, when it comes out negative, it's y. We don't know time. I like to put it down here because remember, it's a scalar quantity and it can be used in both your x and your y. I know my velocity initial in my x is 3.5 meters per second. Velocity initial in my y is 0. Alright, I know 3 values in my x, but doesn't actually have enough. In your lab, the way we're going to do this is you're going to find your velocity initial by rolling a ball and measuring it. We'll use our lab quest and do that. And then that'll be your V initial for your launch. And you have to tell me how far away it'll land. So I actually think that would be slightly more simple than this, because if we actually knew our y, which again is what you would do in your lab, you know how high the table is, it would be a simple third kinematic, find the time, plug it in, find the x. This one was a little bit more challenging. So if you got to this point, that is great. But now what we need to do is we've got this, and this. Yes. Let's see what we can figure out. Alright. Now technically we have 3 here, but because the acceleration is 0, it's not going to get as much. Because we don't have time. But we know this gives us an indication of how much time it was actually in the air. That's the only indication we have. So we know we're going to end up using that. So let's just look at a few equations we know. We know delta x is equal to v initial, which is 3.5 meters per second, times time, which we don't know time yet, but I'm going to rewrite this to, so you can see better why I've simplified it that much. Remember, the third kinematic would be delta x is equal to v initial times time plus 1/2 at squared. in the x for any of the scalar quantities. But if we plug in what we have, we'll see that acceleration being 0 means this falls off, because if you're adding 0, and anything times 0 gives you 0, we're going to have 1.5 meters for our delta x is equal to our v initial, 3.5 meters per second, times our time, which we can actually solve for. Now we're going to divide both sides by your 3.5 meters per second to get time by itself. Oops. Okay, so I'm going to actually perform this mathematical operation quick. And I'm going to have 1.5 divided by 3.5. Alright, so my time is 0.43 seconds. Alright, now I can use this time, and again, because it is a scalar, the time is in the air for both. When it hits here in the x, it hits there in the y. When it launches here in the x, it launches in the y. Okay, it's a scalar quantity, the direction didn't matter, and time travel doesn't exist. Okay, so pause if you don't want me to erase yet. I'm going to erase my values. Is Asher playing? Ah. I'm going to rewrite that. Oh, it's actually my given here too. Okay, that's fine. It's down below here, which I got just with the answer key did. Alright, so now I can actually use the kinematic 3, but this time we're going to say delta y is equal to my v initial in my y times time plus 1/2 at squared. Under y value, y value, y value. We cannot have any x values. So my delta y is what I'm solving for, is equal to my velocity initial, my y, is 0. Here it is. So that is going to cross off, because 0 times t gives me 0. 0 plus anything, this becomes irrelevant, is equal to 1/2 acceleration of y, acceleration due to gravity, t squared. Oh, I'm actually going to plug in my t squared. Alright, so it's 0.43 seconds squared. Let's go ahead and type this on the calculator. My clear button doesn't show on the smaller version. Alright, so we're going to say 0.5 times negative 9.81 times 0.43, and see how easy it is to miss that square, especially when I've got it all tight in there. Alright. Now you'll see the answer said positive number. Alright, my delta y is negative 0.91 meters. Okay, so just shy of a meter is what I dropped, but it asked how high is the table, so that's why the value they gave you is positive, because even though it dropped 0.91 meters, that means that the table was 0.91 meters tall.